Hello and welcome to Shridevi Classes YouTube channel where we inculcate interest and confidence in engineering subjects. Today in our playlist Induction Motor we will study speed control of three-phase induction motor. In previous learning video we have studied stator side speed control of three-phase induction motor. Today in this video we will study three different methods used with slip ring type of motor having phase wound rotor, and we will study how addition of rotor resistance or injection of slip frequency EMF or cascade operation of two slip ring motors can achieve speed control of induction motor. Let's start. Electric motor shown in this blue ellipse is three-phase squirrel cage induction motor, which is most popular electric prime mover used by our world due to its economic, rugged and almost maintenance-free basic design and operation. More than 90% motor used in industries are of such three-phase squirrel cage induction motor. At no load conditions, the rotor of induction motor rotates almost at a speed of rotating magnetic field, synchronous speed, and the speed difference of rotating magnetic field and motor rotor is just 0.5% of synchronous speed, and at full load conditions this speed difference may become 5% or 6%. So we can say motor in its entire operation zone from no load to full load have a very small speed regulation, that's just 5-6% of synchronous speed, and we can say induction motor is almost a constant speed motor. That's why majority of industrial, agriculture and other sector activities use induction motor for constant speed operations. But in some industrial applications we may require speed variation or speed control of such motors, and for that we have to use special measures to obtain speed control in such three-phase induction motors. Let's understand theory of speed control in an induction motor. In an induction motor, when three-phase space displace winding is excited by three-phase time displace excitation, then between stator and rotor in the air gap a rotating magnetic field of constant magnitude and constant rotating speed get produced. Now the speed of rotation of that rotating magnetic field is called synchronous speed, ns in rpm, and that speed depends upon the frequency of three-phase supply given to stator f and the number of pole for which stator and rotor are designed, that is p. So for f frequency and p number of pole, the rotating magnetic field speed called as synchronous speed in rpm is given by 120 f over p. Now due to electromagnetic induction and speed difference between rotating rotor and rotating magnetic field, current are induced in rotor and those induced current interact with rotating magnetic field and rotor start rotation by electromagnetic torque developed in rotor in the direction of synchronous speed with a certain amount of speed difference, and that speed difference is represented by slip, and for s amount of slip then rotor speed nr in rpm is given as ns 1 minus s. The rotor speed in rpm is given by this relation represented in this blue frame clearly indicate that we can change rotating speed of induction motor rotor by either changing rotating speed of rotating magnetic field ns by change of supply frequency or change of number of pole in rotor winding, or we can also get speed variation in induction motor by change of slip. Now the slip depends upon equilibrium of motoring torque and load torque as per torque slip characteristic, but by certain means we can modify or change torque slip characteristic of induction motor, and by that change for the same amount of load we can get different amount of slip and different amount of rotating speed. So speed of induction motor can be changed by either by changing frequency of supply to stator or number of pole in stator winding, or by the change of operating slip in induction motor. In this blue ellipse, the rotating speed of induction motor rotor in rpm is related to synchronous speed of rotating magnetic field and operating slip of motor by this yellow highlighted relationship, and this relation clearly indicates that we can control speed of induction motor by either control of synchronous speed of rotating magnetic field, and that can be controlled by change of supply frequency given to stator winding, or we can have special designed stator of induction motor where we can change number of pole in stator winding, and we can also change torque slip characteristic of induction motor by several means, and by that variation in torque slip characteristic for the same amount of load torque we would have a variation in operating slip, and variation of slip may result in variation in operating speed. So speed of induction motor can be changed by 5 popular methods: the change of supply frequency to stator or change of number of pole in stator can change synchronous speed of rotating magnetic field, and by that we can control speed speed of induction motor, and we can also change torque slip characteristic of induction motor, and by the change of slip operating speed of induction motor can be controlled. And this change of slip or slip torque characteristic can be achieved by change of just stator applied voltage without change of frequency by simple convenient tools, that is called stator voltage control. And if our motor is slip ring induction motor, then we can also change slip torque characteristic by insertion of extra resistance in rotor circuit across slip rings in a phase wound rotor, and the same type of characteristic can be achieved by injection of slip frequency EMF in rotor circuit. Now a special method can also be used in two slip rings motor when they are cascade operated. Now all these speed control measures are also classified on the basis whether the control is achieved from stator side or from rotor side. Now the change of frequency in stator winding or change of number of pole in stator winding or supply of variable voltage to stator winding is called stator side control of speed in an induction motor. The other method, that is extra resistance in rotor circuit or injection of slip frequency EMF in rotor circuit or cascade operation of two slip ring induction motor, are speed control measure of rotor side, and such rotor side speed control can only be used for slip ring type of induction motor which have a phase wound rotor. So such control known as rotor side speed control. Popularly there exist three methods for speed control of induction motor from rotor side, and one among them is the simplest and most popular rotor circuit resistance control, where in phase wound rotor across slip ring we insert extra three-phase balance external resistance and change per phase winding resistance value to change torque slip characteristic, and that results in control of speed of induction motor. Now another method is we inject slip frequency EMF in rotor circuit, and injected EMF may be in phase or out of phase of rotor induced EMF, and that control operating speed of induction motor. And there is also cascading of two slip ring induction motor in such a way that their cumulative or differential cascade operation produce altogether different stepped change in operating speed. But important point is that these three method of rotor side speed control can be applied only to slip ring type of motor having phase wound rotor, because in squirrel cage motor the metallic cage of rotor is closed by short circuiting end rings from both sides, and there is no provision of adding extra resistance or EMF injection in those squirrel cage motors. So rotor side speed control of induction motor is possible only in slip ring type of motor having phase wound rotors. Let's study these three methods one by one. The most common and convenient speed control of slip ring induction motor from rotor side is rotor resistance control. Such rotor resistance control cannot be applied to squirrel cage induction motor where cage winding is short circuited from both sides by end rings, and there is no provision to insert extra resistance in rotor circuit. But whereas in phase wound rotor, in rotor core slots, a double layer distributed three-phase space displaced winding is made for same number of pole as that of stator side, and this three-phase winding is star connected, and the star point is insulated and placed safely with insulation and bracing within winding rotor, and winding is star connected, and three ends of star connected three-phase are brought to insulated slip rings, and on those slip rings carbon brushes are placed in brush holder to make connection of external balance three-phase variable resistance to rotor circuit. Just like squirrel cage induction motor, the stator of slip ring motor is also wound for three-phase 120-degree electrically space displaced distributed winding in stator core, and the stator winding is delta connected for normal running operation, and three-phase supply is connected to stator winding terminal by three lines. Rotor is again wound with three-phase space displaced winding with poles equal to stator winding pole, but winding is star connected, and three end of star connected winding are brought to three insulated slip rings on the shaft, and over slip rings carbon brushes are used to connect a three-phase variable balance resistance to rotor winding circuit. And when this external resistance is varied and controlled, the per phase rotor resistance of three-phase wound rotor of this slip ring induction motor gets changed. That change slip torque characteristic of induction motor, and for certain load torque when slip gets changed we got a controlled change in operating speed of slip ring induction motor. The motoring torque and rotating speed characteristic of three-phase induction motor is shown here, and when slip ring is short circuited there is no extra resistance and winding got its inherent per phase resistance R0. then torque speed characteristic is shown by this blue characteristic, and when extra resistance is added across slip rings and per phase rotor resistance is made 2 times R1, then this characteristic will shift to this black characteristic, and increase of per phase rotor resistance 2, 3 times, 4 times or 5 times will shift characteristic as shown here, and these characteristics clearly indicate that the maximum torque produced by 3-phase induction motor doesn't depend upon per phase rotor resistance. It only depends upon applied voltage and standstill leakage reactance, and since the two, applied voltage and leakage reactance, is constant, so maximum torque capability of induction motor remains the same irrespective of change in per phase rotor resistance, but the slip at which this maximum torque occur, that is called S maximum, do change when we add extra resistance in rotor circuit, and when extra resistance is doubled, the slip of maximum torque also get doubled. It clearly indicates that when SM increases, the stable region of characteristic where torque and speed got negative slope increases, and this increase inherent speed regulation available in characteristic, and that can be used to control speed of induction motor. As we add extra resistance across slip rings in phase wound rotor, the characteristic shifts to another position, and accordingly for same amount of torque, operating speed will change and will have lower speed value with increased slip conditions. So with increase of per phase rotor resistance, when we add extra resistance, characteristic shifted, and for the same motoring torque, the slip of operation increases, and that reduce operating speed, and by this way we can control speed of induction motor by increasing extra resistance across slip ring. But even when motor is operating at lower speed positions, the maximum torque capability of motor remains the same. So this method is very popular where we need good torque capability and reduce speed operation like crane, hoist, and this process of adding extra resistance in rotor circuit at slip ring is very simple, quite convenient and economic in operation. Another significant application of slip ring induction motor and addition of extra rotor resistance can be noticed at the time of starting. Without extra resistance, when slip ring is short circuited, motor produces a small amount of starting torque, and since starting torque of induction motor is directly proportional to per phase rotor resistance, when we add extra resistance and per phase rotor resistance get doubled, the starting torque also get almost doubled, and likewise increase of extra resistance keep on increasing motoring torque. But and at R4 condition, the per phase rotor resistance and standstill rotor leakage reactance become equal to each other, and maximum torque condition SM occur at slip 1, that means at start position, and entire speed torque characteristic got a negative slope, and that becomes stable. And if we further increase rotor resistance, we will find that SM become more than 1, and in that case starting torque, which was earlier keep on increasing, attain maximum value at R4 and will reduce for R5 value. So at R4 resistance value we got maximum starting torque, and further increase of rotor resistance from R4 to R5 will decrease starting torque as shown here in this characteristic. But the significant fact is that when we add extra resistance in rotor circuit, it increase rotor impedance, and that decrease starting current. So addition of extra resistance in rotor circuit of slip ring induction motor improve starting performance by both way. It increase starting torque and reduce starting current. One should notice a practical fact that external resistance used for starting purpose got a short time rating, whereas extra resistance used in slip ring motor for speed control may require a continuous rating. So extra resistance used for speed control are costlier, having higher heat dissipation capability, whereas extra resistance used only for the starting are designed with economy and they have only short time rating. Now this method of insertion of extra external resistance in rotor circuit across slip rings is quite convenient and simple in operation, but it also got some disadvantage. One disadvantage is such method cannot be used for squirrel cage type of motor where rotor cage winding is already short circuited by two end rings and there is no terminal available to insert extra resistance in rotor circuit. So this method can only be used to slip ring motors only, and in comparison to squirrel cage motor, slip ring motor not only bit costlier, need more maintenance, and slightly due to higher amount of leakage reactance, its running performance is inferior. Another disadvantage of rotor resistance method of speed control of slip ring induction motor is increased amount of losses in extra resistance, and that make it wasteful and reduce its efficiency, as during operation from stator to rotor a constant air gap power is available. But when we add extra resistance in rotor circuit and increase slip of maximum torque or increase stable negative slope torque speed characteristic zone of induction motor to get reduced amount of speed at higher slip, the rotor copper losses increases with increase of slip, and when slip get doubled, rotor copper losses get doubled, and if slip get 4 times, rotor copper losses become 4 times, and that reduce mechanical output from the same air gap input. So this increase losses and reduce efficiency. A better fortunate part is that increased additional copper losses take place to external side, and that won't make trouble with temperature rise or heat dissipation. Another disadvantage is that when we increased rotor resistance and got higher slip operation and reduced speed, the inherent speed regulation get increased, and at this position a slight change in load torque results in higher amount of speed variation. So increased slip or reduced speed operation has poor speed regulation. Since extra resistance connected to slip rings across brushes got a continuous operation duty, so they should have very good power dissipation capability. Usually we use water-based rheostats for these extra resistance used for speed control of induction motors, or recently modern thyristor power controller are used to achieve such variable resistance property with convenient and economic power dissipation capability. Let's understand that. A large size squirrel cage induction motor need a heavy duty external 3-phase balanced variable resistor of very good power dissipation capacity, and these external rheostats are normally water based rheostats. But in place of a complex 3-phase balanced variable resistor, we can use a fixed single resistor of heavy duty and higher power dissipation capabilities, and we can use a chopper drive. And in this solid state alternative arrangement, the slip frequency 3-phase alternating current is rectified, and rectified DC is sent to this resistance, and this resistance is made variable using a chopper duty cycle control. When chopper is on, resistance becomes short circuited and energy gets stored in this inductor, and when chopper is in off state, that stored energy and rotor circuit energy passes through resistance, and we can control duty cycle and control amount of variable resistance load applied across slip rings and control speed of this wound induction motor. Now this method is not only economical, require less maintenance as compared to water based rheostats. Another way to control speed of slip ring induction motor is to inject slip frequency EMF in rotor circuit, and that injection of EMF can alter rotor currents, and that current change torque capabilities of motor, and that is used to control speed of rotation. And this method of injection of EMF in rotor circuit makes this squirrel cage induction motor really a doubly excited induction motor, where electric supply is given to both stator at means frequency 50 Hz and to rotor at slip frequency SF, which depending upon slip may be half an Hz to 2 Hz. Now a step down transformer reduce voltage level, and a converter having rectifier and inverter supply slip frequency EMF to rotor circuit. Now the injected EMF got same frequency as of EMF induced in a rotor during rotation, but the phase of injected EMF and rotor EMF may be in the same phase or in opposite phase, and depending upon that phase condition, the speed of induction motor is controlled by injection of EMF in rotor circuit. When injected EMF having same frequency as that of rotor EMF is in opposite phase to rotor EMF, that oppose flow of current in rotor circuit, reduced rotor current, reduced torque and reduce operating speed, and this opposite phase slip frequency EMF can be used to reduce speed. Similarly, if we inject slip frequency EMF in coil cage rotor with the same phase as that of induced EMF in rotor, then the two together increase rotor current, that increase torque and speed of operation. So this method of injection of slip frequency EMF in rotor circuit in phase or opposite phase can control speed of induction motor, and by suitable phase difference between rotor self-induced EMF and injected EMF, we can control speed to the both side of base speed. It can reduce speed from base speed, or it can be used to increase speed from base speed. And with modern power electronic devices, this is achieved without losses in extra resistance. So it is not only convenient, durable, but also energy efficient. Another conventional method of speed control of slip ring induction motor is cascade operation of two slip ring motor. But this cascade operation of two slip ring induction motor can change or control speed only in stepped manner, and in this cascade operation we need two slip ring induction motor. One motor is called as main induction motor, and stator of that is supplied with three-phase mains supply of rated voltage and rated frequency, and the other motor known as auxiliary induction motor is again a slip ring motor, but its stator is supplied with slip frequency EMF produced by rotor of main induction motor, and we have a provision to add extra resistance in the rotor circuit of auxiliary motor. Now both main motor and auxiliary motor are mechanically coupled and connected to the same shaft on which load is placed. So both main motor and auxiliary induction motor has to run at the same speed. Since main induction motor is supplied with rated frequency supply, so its own rotating magnetic field rotate at normal synchronous speed, and that maintain a certain amount of slip with rotating rotor of such a manner that slip frequency EMF supplied to stator of second motor generate a rotating magnetic field of slip frequency speed, and both rotor, which are mechanically coupled, rotate motor at the same speed. Now this connection is also called as tandem control, and since it requires two motor for one operations, so nowadays this method become obsolete now, because modern static chopper controlled rotor rheostat method or variable voltage and variable frequency supply to stator are far better, efficient, simple, convenient and economic method of speed control than this tandem control or cascade operation. But earlier, when power electronic technology was not available, these methods were popular in industries, and there are two cascade operation. One is called cumulative cascade operation and other one is called differential cascade operation. When the rotating magnetic field of main motor and auxiliary motor both operate in the same direction to produce torque of both motor in the same direction, then this method, which add torque of two motor on shaft, is called cumulative cascade operation of two slip ring induction motor. Now in this operation, equivalently the rotor of two mechanically coupled slip ring induction motor has to rotate with a speed of a single motor having P1 plus P2 poles, and since number of pole in equivalent machine has increased, so that has reduced the operating speed. So with cumulative cascade operation we get stepped reduction in operating speed, whereas when phase sequence of auxiliary motor is changed, the torque of two motor, main motor and auxiliary motor, now become in opposite direction, and this method is called differentially cascade operation of two slip ring induction motor. And in this condition, the speed of two differentially cascaded operated induction motor is equivalent to a speed of single motor having P1 minus P2 number of poles, since number of poles, if P1 and P2 are not identical, has reduced. So with reduced number of pole, the motor operating speed has increased. We can understand this by an example too. Let main motor got P1 number of pole and auxiliary motor got P2 number of pole, and P1 is not equal to P2, then we can get four different speeds when only motor A is connected to supply and second motor is not used with electric supply. Then this system will operate at P1 number of pole conditions with this synchronous speed. It maintain corresponding 0.5% to 5% slip operation from no load to full load and operate at one speed. Now if auxiliary motor got P2 number of pole and only that is connected to supply, then corresponding to its synchronous speed of P2 number of pole, our system can work on another speed. And if two motor are cumulative cascaded, then they are equivalent to single motor of P1 plus P2 number of pole, and since pole number has increased, it has reduced speed. And similarly, when two motor are differentially cascaded, then speed of set become speed of a single motor of P1 minus P2 number of pole, and this will produce the maximum speed of operation at less number of pole. Say for example, P1 is 6 Hz, P2 is 4 in number, and supply frequency is 50 Hz. Then when only main motor is functioning with 6 number of pole, the synchronous speed is 1000 rpm and motor runs at 995 rpm to 950 rpm conditions from no load to full load. And if we use only auxiliary motor with 4 number of pole, then our synchronous speed become 1500 rpm for frequency 50 Hz, and corresponding to that we have running speed from 1490 to 1420 rpm. And if two are cumulative cascaded, then this become a system of 10 number of pole having synchronous speed 600 rpm, and corresponding to that we have lowest speed operation. And if two are differentially cascaded, then P16 and P24 results in as a difference 2 number of pole machine, and we would have a rotation of 3000 rpm synchronous speed operation. So we got maximum speed with differential cascade or minimum speed with cumulative cascade operation, and two different speeds for P1 and P2 number of poles. So we can get 4 different speeds by this cascade operation of two motors. We have explained all 3 rotor side control of speed control of 3-phase slip ring induction motor. Now you understand how addition of rotor circuit resistance change torque slip characteristic and achieve speed control, or the most efficient slip frequency EMF injection in rotor circuit can achieve speed control to both side of basic speed. And now you also know what is cascade operation. Our other learning video on stator side speed control of induction motor or variable frequency drives for speed control of 3-phase induction motor are also very useful to understand speed control of induction motor in a complete and comprehensive way. Our other learning video of this induction motor playlist will improve your understanding and confidence about working and application of induction motor. And other playlist of Sridevi classes YouTube channel, especially power electronics and power system, are also very useful. If you like our work, do share it with your friends. And for study material and online classes support, do join membership of Sridevi classes. Happy learning. Thank you very much.